Hello, so today we are going to do this problem, partition list. So the problem asks us to, given a head of a linked list and the value x, we want to partition this linked list such that all the nodes smaller than x come before, and all those greater than x or equal come after x. And we want to, at the same time, preserve the original relative order. So among those smaller than x, we want to keep the original order, and similar thing for those greater or equal than x. So that's the problem here. So let's look at this example. So we have this linked list and x is equal to 3. So 1 is smaller, so it stays here. 4 bigger, it goes to the right. 2 smaller, we bring it here. This 2 also smaller, we bring it here. 4 bigger, we bring it after. And 3 big equal, so it's on the right, and 5 bigger, so it's on the right as well. Now you notice something. For 4 and 3 we kept the same order, right? Yeah, so that's pretty much the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this. So this here is the linked list, so it may be harder with all of the pointers to think about the solution, so we can just go to a simpler version, which is using an array, and see how can we come up with a solution. And that's a trick that we should often do, is if it's a little bit complicated, pick a simpler problem, solve it, and see if that solution applies to the more complicated one. So if we copy the array that we have here, what would be if it's just an array instead of a linked list, how would we solve it? And x equal to 3. So the easiest way to do it is, of course, to just to have 2 arrays, right? One for smaller values and one for those that are greater or equal, and just traverse the array and put those smaller in less and those bigger or equal in GE, and then concatenate the 2 at the end. That way we'll preserve the original order because we add them in the same order as in the array, but at the same time we'll partition. So if we take a look here, 1 first, it's smaller, so we add 1. Now we go to 4. 4 is bigger, so we add it here. We go to 3. 3 is equal, so we add it here. We go to 2. 2 is smaller, we add it. 5 bigger, we add it. 2 smaller, we add it. And so we concatenate both, and at the end we get, so we return just less plus GE, right? So that's the solution here. Okay, so now that we know the solution in an array, how can we apply it to a linked list? Well, we could actually just do the same thing, create a less header, except instead of an array, it would be a less head, and instead of an array here, it would be, and each time if we find a smaller element, make it the next of less make it the next in the less head list of nodes, and if it's bigger or equal, make it the next for those bigger or equal. And at the end, just make so let's say we construct those smaller, and we construct those bigger. Maybe it's something like this. So at the end, what we need to do, so we will have a pointer here for the current traversal on less, so let's call it less, and we would have 1 for GE, and we would have 1 pointing to the head of GE. So what we can do is just make this one, the next of this one, be this one. Okay, so what do we need here? So we need 2 things. We need for each of them. So for less, we need something that points to the head, and we need something that points to the last node we added, right? So that when we are done, we can just make the next of the last node we added be the head of those greater or equal. And we also need the head of greater than equal, because we need to point less that next to it. And the current, we don't need it, we need it just as we are constructing greater or equal, right? So let's apply it and see what this would mean here. So if we take this linked list, let's bring it here. So what would that mean? So since at the end we want to return this head here, let's just have a dummy node that points to it, so that we can say dummy.next, right? So let's have less dummy, call it dummy, right? And have greater or equal dummy as well, right? And this one would have maybe node -1 and this one -1 as default value, right? And now what we can do is have a current pointer here that looks at these values. So if we find that current value is smaller than x, right? Then we need to add the value here. So we can create a new node with value 1, right? And make basically less. So less pointer was here before. So make less dot next, we'll point to this new node. So create a new node with current dot val. Okay, and now less moves here. So less helps us construct this list, and less dummy node is here, helps us get the start of the linked list here. Now we go, current is at 4 now. It's bigger, so same thing as we did here. We say GE, which first is pointing here, dot next is going to be equal to list node of the current dot val. Okay, and so we put 4 here, and we move the node, we move the pointer for the current node for greater or equal to the one we just added. So each time we need to do GE equal to GE dot next, and here less equal to less dot next. So each time we check it's smaller or equal, we add it to the corresponding linked list, and we advance the pointer. And now we advance current again. It's 3. 3 is equal, so we need to add it here. And we move our GE pointer here. And now we go here, current 2. 2 is smaller than 3, so we add it here. We move our list pointer here. Now we are at 5. 5 is bigger, we add it here. We move our GE pointer here. And then after that, 2, and we move our last pointer here. And now at the end, what should we do? Well, we need 2 to point to 4, right? So we could just say at the end, last dot next is going to be equal to the head of GE. How do we get the head of GE? It's just the dummy dot next, right? Because dummy is just placeholder here. And at the end, what should we return? Well, we should return this, the head here, and this is just last dummy dot next, right? So we can just return. So you can see it's very similar to the array solution, except here we are working with linked list instead. So instead of constructing an array, we construct a linked list, and instead of concatenating an array, we point the less part to the head of the greater or equal part. Yeah, so that's pretty much it. Now, except here you can find that we created a list node each time. We actually don't need to create a new one. We can just put current, right, that we are at, and then because next time we'll do less dot next and we'll change it, it will change the pointer, and so we don't need actually to create extra memory with these list nodes. But starting simple, use list node, and then from there we can move to using current. In terms of time complexity here, this is just traversing the linked list, so it's O(n) time. In terms of space, we are using 2 extra linked lists, so O(n) space. And that's pretty much it, so O(n) time, O(n) space. Now let's write this down and make sure it passes test cases. Okay, so let's write down a solution here. So first we need a couple of pointers. We need current that points to the current node we are looking at in the linked list. And we need something that, a dummy node that points to the smaller portion. So let's call it less dummy. And we could just add a sentinel value of -1 here. And we need a similar one for the greater or equal part. So let's just call this GE like this. And now we need a pointer that moves through the current node of less portion, and one for the greater or equal portion. So let's call them less. So less is going to be, starts out at that, at this, and then GE, which starts out as this. And now we need to traverse our linked list. So while there is a node, right, we haven't reached the end yet, we check the value of current. If it's smaller than x, then we say less.next. Let's first start with the version where we create a new node. So create a new node and we add the value. And then we need to move our pointer, right, to the one we just added, so that next time the next element is going to be the next of the one we just added, right? And then we check if current.val is bigger or equal, then we want to add it to the greater or equal portion. So we say ge.next is going to be equal to, similar to the less portion. And then we say .next. And now we move at the end, once we found the place for the node, we need to move the pointer on the original linked list. And now, to know what to return, we will just point the end of less portion to the beginning of the G portion, which is the greater or equal portion, which is just the dummy node that points to the head. We do .next to get the head of the greater or equal portion. And at the end, we want to return the head, which is just the head of the less portion. And so we could just, to get that, we could just do .next, because that points to the head of the less portion. So let's first try out this solution. Okay. Let's submit. Okay, so that passes test cases. Now, as I said, we don't need actually to use this extra memory. So we can do is just point to current. And what will happen, you may say, okay, but current has also its next portion, right? But what will happen is that we will go to less.next, and then in the next iteration, we will replace it, right? However, one thing is, since we point to current here, greater or equal .next may have some values, right? So we need, at the end here, we need to say greater or equal .next, we need to set it to none, right? So that we don't have, let's say if the last greater element was in the middle of the linked list, because we said current, we don't want it to still be attached to the next. And since our loop will be done here, we won't do ge.next again, right? So we want to prevent having a rest of the original linked list in it. And so that's pretty much it. Now let's run this. And let's submit again. And that passes test cases as well. Yeah. So that's pretty much it for this problem. Thanks for watching. If you found this video useful, please like and subscribe, and see you on the next one. Bye.